we were originally going to just do a presentation on refrigeration and air circumstances. We thought it might be better to do something floating around energy efficiency in refrigeration and air conditioning systems. It's a huge area. We've got, what, 20 minutes or something, so we're only going to very vaguely scrape the surface. But we'll work through the whole thing. Please ask questions as we go, or alternately at the end, my email address is there. You can send on any queries and we'll answer as best we can. Okay, so what we're going to go through, we're going to go through refrigeration. Basically, what is it? Why is refrigeration different from air conditioning? Roughly, very high level of how it works, and then we're going to look at energy consumption in refrigeration, which is considerable, and we're going to look at reducing the energy consumption. And then on air conditioning, we're basically going to go through the same things again. So we'll start skipping on. This is our thing actually here for the last copy of this, I presume, for results. So refrigeration, in its purest definition, is the removal of heat from a material or space so that its temperature is low and out of its surroundings. A damp cloth around a bottle of beer is a refrigeration process. A cooling tower is a refrigeration process. What we're particularly interested in here is the vapor compression system. That's mechanical refrigeration systems. So the areas can be divided into three basic areas: the domestic refrigeration, what you've got in your house, and don't think you can't save money on those by some basic maintenance. At the back of your fridge, there's a black coil. It's called a condenser. It's the thing that the heat comes off. It's reckoned you can save up to €70 a year just by cleaning that. So I'd suggest you all do that today. It's a night out. Commercial refrigeration, probably the biggest part of the industry. Refrigeration systems used in commercial environments, shops, supermarkets, bars, etc. Usually subdivided again into high temperature and low temperature. The high temperature, low temperature division is, high temperature is still quite low. So you're looking at kind of, in shops, you're looking at -2, +4 area, +8 would typically be kind of beer pubs. And then you have the freezers, -18, -20 range. And then you have it's basically large food processing, meat plants, dairy. Most of those are ammonia refrigeration systems, liquid overfeed. But you do include HFCs in those depending on their size. So the whole thing is based on latent heat and using it to move heat from one location to another. So the vapor compression system uses the latent heat of a refrigerant to move heat from one location to another. So how we do that is in the evaporator, we cause a liquid refrigerant to turn into a vapor. And in doing that, it absorbs heat. In the condenser, we do the exact opposite. We change that vapor back to a liquid, and in the probe, it gives up heat. So the four components in the system, the four components matter an awful lot when we're dealing with energy. The compressor, it increases the refrigerant vapor pressure and saturation temperature. It's the biggest single energy user on the system. The condenser cools the refrigerant vapor to below its saturation temperature. It's basically a heat exchanger, whereas it's a passive device. You don't really a whole lot can go wrong with it, barring leaks. It does have a big role to play in energy efficiency. The expansion device, which reduces the refrigerant's liquid pressure and saturation temperature, basically it's the opposite of the compressor. And the evaporator, which absorbs heat, causing the refrigerant to change from liquid to refrigerant vapor. And that's our basic cycle. Okay, so the cycle runs, I don't know if you can see you can't see my mouse on this. Basically, the refrigerant's coming out the red line from the compressor. That's the discharge line. It's a hot, high pressure vapor. It enters the condenser where it's cooled and then reaches down to its saturation temperature, which is its boiling point, and turns to a liquid. Following that, it goes down the liquid line and hits the expansion device. That's the TX valve there. That's where the pressure is dropped. So that's the opposite, does the exact opposite of the compressor. and the refrigerant boils or changes from a liquid to a vapor in the evaporator, therefore absorbing heat, it is then when it's all vapor, stuck back to the compressor and the cycle starts over again. That's a very, very brief and short introduction to how the cycle works. Now, typical energy consumption. I looked in particular at supermarkets because they have so much and such a variety of refrigeration plants. So as you can see on that, refrigeration on the average supermarket is nearly half of the electrical consumption. In some supermarkets, it's higher. I've heard of figures going up to 70%. This particular one was taken before we started moving more, or these figures were taken, started moving more to LED lighting. So the lighting, you can assume, would drop. The AC and ventilation is obviously another huge load, and then just other equipment on it. So there is obviously massive savings to be made if we can reduce the cost of running the refrigeration system. So the compressor, it consumes about 80 to 90% of the electricity in a typical system. The condenser and evaporator fans, along with any pumps or anything like that in you have in it, plus the control system, makes up the remaining 10 to 20%. So, how to improve the energy efficiency? The obvious one, reduce the heat load on the plant. That isn't saying put less equipment in, it is saying close doors. Use door curtains, select refrigerated cabinets with doors. I have a bugbear on this. I can't walk through a supermarket without closing the doors. Really drives me around the twist that people would leave doors open. Look at your set points. If you can increase the set point by 1 degree, you can save approximately 3% in energy. If you don't have to be going down to 2 degrees and you could survive at 4 degrees, there's a potential 6% energy saving there. Clean your condenser coils. A dirty condenser will lead to an increased electrical load on the compressor and the condenser fan motor, as well as increased runtime. If your condenser is dirty, it will cause the head pressure to rise, which means that the compressor will have to work harder to get the pressure up there. It also restricts the airflow across the condenser, which means the condenser fan is going to work harder as well. It's approximately 3% in energy. Cleaning the condenser is the simplest job you can do on a fridge system and one of the most important. Again, clean the evaporator. The evaporator may be a little bit more difficult to clean and people sometimes ignore them, but they do get dirty, particularly in supermarket environments. And again, it's the same thing. If the evaporator gets dirty, it reduces the airflow over the evaporator, causing the evaporating temperature to decrease, which in turn will lead the compressor to have to work harder, and it will also increase the duty on the fan motors. What people rarely do is clean the fan blades. Dirty fan blades are inefficient. The fan blade is designed and its shape is designed to move air as efficiently as possible, and as dirt increases on the fan blades, your efficiency of your fan motors drops. Then you've got defrost systems. Defrosts, they're necessary, you can't survive without them. But if you've got a basic defrost system, i.e. a simple time clock with a timed defrost of 3 or 4 times a day, that can be highly inefficient. So what you need to do with defrost is to get yourself a decent control system that will do things like offer defrost on demand. In other words, if your system doesn't require a defrost, it will sense that and skip the defrost. Every time the system goes on to defrost, what you're doing is adding a heat load into the system, which has got to be removed again by the fridge system. Control systems, I mean, all through the years in refrigeration, control systems have been incredibly important, and it's been a massive area of improvement over the years. So modern control systems will save energy. That's basically why people put in decent controls, is to save energy. It'll offer things like defrost on demand, the use of electronic expansion valves, head pressure control, inverter-driven compressors, all sorts of things which all put together save quite a lot of money. Night setback. Night setback is used quite a lot in commercial refrigeration. The idea is when the shop closes at night, you can actually increase the set point by a couple of degrees. And by doing that, you will obviously save money. You also want to check pipe insulation, door gaskets and cold room insulation. The giveaway for breaking down insulation, if it's the cold room or the pipe, tends to be condensation or even ice forming on the outside of the insulation or the outside of the cold room. Door gaskets are incredibly important. If you have bad door gaskets, you obviously get heat entering the cold floor, but what you will also get is moisture. That moisture will condense on your evaporator, increasing the amount of defrost you require and therefore decreasing the efficiency of the whole system. You can also look at things like putting door curtains on, all this kind of stuff, anything to keep the systems or the cold store sealed. Okay, air conditioning. Air conditioning is defined as the treatment of indoor air in order to control certain conditions required for human comfort or for a process. People tend to think of air conditioning as purely controlling temperature. That is only a part of what you're trying to control. So the conditions you should be trying to control are temperature, humidity, cleanliness, air quality, air pressure gradients, and air velocity. All of those things are included in a full air conditioning system. So temperature control, generally achieved using a mixture of vapor compression systems and utilizing where possible the outside ambient conditions. If you've got a centralized air conditioning plant, you can get a thing called free cooling. It's a method of getting as much cooling into an area as you can without having to run the refrigeration plant. It can be done through your BMS system. There's liquid migration systems that will do it as well. Humidity control can be used to either increase or decrease the moisture content in the air to the desired level for human comfort or for a particular process. For the processes, if you look at things like computer rooms years ago used to come with a humidifying bottle attached. And the purpose of that bottle was that as the computer room air conditioning system was working and the door was sealed, it would be sucking moisture out. Low humidity leads to high static electricity, and that static electricity used to blow, not so bad now, but years ago used to blow the chips on computers. So that good computer room air conditioning systems always came with a means of increasing the humidity. You've also got problems with humidity with people. It can be too high. Typically with air conditioning, people tend to suffer more from low humidity. Low humidity leads to sore eyes, sore throats, itchy skin, all sorts of unpleasant things. I know we tend to ignore it when people say the air conditioning is not making me feel well, but they are probably telling the truth. It's a form of sick building syndrome. Air cleanliness, achieved via filtration systems. That level depend on the application. You know, if you're going into clean room level, you're going up to HEPA filters. Air quality is also incredibly important and ignored. For human comfort, it's important that the CO2 levels are kept to an acceptable level, and that's achieved by introducing a proportion of fresh air into the controlled environment. If you just put a split air conditioning unit into a sealed room and run it, and there's people in that room, the CO2 levels will start rising and people are going to start feeling uncomfortable. You've got to have some form of replacement air changes. Air pressure gradients are used in clean rooms. So typically in clean rooms, we will either increase the pressure on the clean room so that any air infiltration will actually be outwards. So we won't let into the room. But in certain situations, you will also use negative side in the clean room. And air velocity, we've all sat in drafts, it's highly uncomfortable. That has to be considered when you're dealing with this stuff. So what we've got here is a typical air handling unit. I'm sorry you can't see my mouse. So we're going to start, if you can look at the top left on that bit that says fresh air. Okay, so what we've got here is a piggyback system. So it's two air handling units, one on top of the other. Has a few bells and whistles on it. This is a real system. We designed it when I was working in DIT, and it's in there, I presume, still operational. So fresh air comes in, goes through this first. This is basically an enthalpy sensor. It's sensing the temperature and the humidity and the conditions of the air. That is fed back to the BMS system, the building management system. The building management system now knows what the air is like coming in. It also knows what the air is like in the room. So what it's going to do is it's going to change those 3 dampers that you can see there between the blue and the yellow arrows, and it will change the ratio of fresh air to recirculated air entering the space to try and minimize the requirements for heating or cooling. The air is then filtered. It's then forced through preheaters. The preheaters are to temper the air. If it's very cold outside, you may need to temper the air so you don't freeze up. We're then going, this is not on everyone, but this is an energy efficiency thing, an air-to-air heat exchanger. So if you follow the blue line, it's going down through the heat exchanger, and it is extracting heat from the air that has been dumped out of the system and putting it into the incoming air. We're then going through a cooling coil and a heating coil. We go through cooling and heating in that order to provide dehumidification. If you change the order, which you see quite a lot, you will have no means of controlling the high humidities. We then go through the fan motor, through a humidifier, and supply the air into the control space. The recirculated air then is sent back, and we have another enthalpy sensor, and that's effectively telling us what the condition of the air leaving the room is, effectively the room conditions. And that air is hauled through, down through the heat exchanger. A proportion of it is recycled back, and a proportion will be dumped out to the environment. Okay, energy consumption, typical office. HVAC takes up a vast amount of energy. Okay, the refrigeration bit, that would be just, fridges in the kitchens and things like that. But you can see HVAC is a very, very big load. It's actually a bigger load, relatively speaking, than the refrigeration load in a supermarket. This is because you're dealing with so much ventilation as well, and the other loads in an office environment are smaller. There is obviously huge space for saving money on this. Okay, so you've obviously, if you've got a DX refrigeration system, everything we did on the refrigeration side, or most of it did on the refrigeration side, will also contribute to saving energy in the air conditioning area. But there are some additional measures we can do with air conditioning. Temperature set points. They're often too rigidly set. Someone's decided the room has to be at 21. If you've been watching the news recently, you'll know that Spain have insisted that no one can send their air conditioning below 26 degrees. There are other countries in the past that have said you can only set the air conditioning 6 degrees below the ambient. This is because the effect of air conditioning is that if you come in from a warm area and you go into an area that's at 26, it will feel cooler and it will feel more comfortable. We tend to set air conditioning too low in this country. Every degree you're rising at roughly 3% in energy. You can also put in weather compensation systems. Weather compensation systems are used also in domestic heat pumps. But the idea is you're monitoring the outdoor air conditions and you adjust the air conditioning system to both not provide too much heat or too much cooling when it's not required, or to change chilled water set points, things like that. Building management systems, absolutely key. On a large system, it's the single most important item for saving energy. Please forgive my spelling on this this presentation. It was put together fairly fast. It's important that it's working correctly. People don't spend enough time worrying about maintaining the building management system. They think it's just going to work perfectly all the time. It won't. Sensors will fail. People will change set points. Actuators will fail. There's going to be all sorts of things. You have to monitor it all the time. You have to make sure it is maintained. Clean and replace filters. Filters will obviously cause an increase in energy consumption across fans as they get dirty, and they'll reduce the effectiveness of the system as well, so it'll cause you all sorts of problems. And people should consider upgrading their air conditioning system. I know it's very nice if you've had even a little split in your office for the last 15, 20 years, and it's been working perfectly, but I can guarantee you it's not working anywhere near as efficiently as a unit you put in now. You will save money by upgrading your system. Then the obvious one on energy consumption, close the bloody window. It's amazing how many times you walk into places and they'll have the windows open and they're trying to heat or cool the system. That's it. We're doing on time. I haven't got 5 minutes early this time. If anyone's got any questions, please contact me. Feel free. I think Stephen has a copy of this presentation, which he'll make available. And I think he was recording this as well. Okay. Thank you very much.
Thank you, John, and thank you everyone for joining. And as John said, everything will be up online. I'll send out the slides to everyone and the link to the recordings as well.
Okay, thank you.
Thank you very much, and see you the next one.